Okay, so this is question number 3 of the Magnetic Fields homework booklet. So in question 3 what we've got is we have a diagram down here and it shows a magnet that's placed on top of a top pan balance, so basically on top of a set of weighing scales. Across this balance is a fixed horizontal wire and a current can flow through this wire if we need it to. This wire passes centrally through a magnetic field parallel to the pole pieces. When we're told that when there's no current flowing, the balance measures a mass of 201.32 grams, and when we put 5 amps through this wire, the reading on the balance goes up and it goes up to 202.86 grams. So in part A, we're asked to explain why the reading on the balance goes up. So there are basically 3 points to this. So number 1, we're starting off at the beginning, so we're explaining why this happens. So when a current flows through a wire, a magnetic field is induced around the wire. So we now have a magnetic field around this wire. This magnetic field interacts with the magnetic field from the magnet, so therefore there's a force on the wire, and this force is upwards. If the force on the wire is upwards, there's an equal and opposite force on the magnet, and that's downwards, and that's why the reading on the balance goes up. We're then asked to state the direction of the current flow and explain our answer. So to do this, we're going to use Fleming's left-hand rule. So if we go back to our picture, what we have is we know that the force on the wire is upwards. So you take your Fleming's left-hand rule, left hand, and you point your thumb straight upwards. The field goes from north to south, so that you turn your hand round so your thumb is upwards, but your finger is pointing towards you. And if you do that, then quite uncomfortably, your second finger is pointing from right to left. So therefore, to answer our question, if we're going to state the direction of the current flow, it goes from right to left. And to explain how we got it, well, we say that the force is upwards and the field is, if you want more detail, the field is coming from north to south, so therefore by Fleming's left-hand rule, the current must be right to left. So in part 3 of this, we're now given some extra information. We're told that the length of the wire inside the magnetic field is 60 millimeters, and we're asked to estimate the flux density. So basically we're asked to calculate roughly what the flux density of this magnetic field is. Well, again, if we go back and think about the forces on the wire, the force upwards on the wire is just equal to B times I times L, and that must be equal to the force downwards, and we can measure the force downwards in essence because the force downwards is proportional to the mass. So the force that's on the magnet is equal to the change in mass that we measure on our balance multiplied by the gravitational field strength. So this force equals this force. Now we know all of the terms in this force apart from B, which is what we want to work out. We can work out the change in the mass on our balance because we're given that in the question, and G is just the constant we know. So if we use this, the current is 5 amps, the length is 60 millimeters, but we've written it in meters instead. The change in mass is 1.54 times 10 to the minus 3 kilograms, and that comes from our information right at the beginning of the question. So we're told that the difference in mass when our current is on compared to when it's off is, so we've got 202.86 grams. If we take 201.32, that's how much the mass has changed by. So that's our change in mass down here. And if we multiply that by G. If we do that and rearrange our equation, we get B is equal to 0.050 Teslas to two significant figures. Finally, in part B, we're asked to sketch a graph to show how we'd expect the balance to change, the reading on the balance to change if we change the current in the wire. Well, if we go to our equation, basically the same equation that we've just had, the change in mass is equal to the force on the wire divided by G. Now, the magnetic field from the magnet stays the same, the length of the wire stays the same, and G is a constant. So that means that I and the change in mass are basically, there's a linear relationship between these two. So if this goes up, then this goes up. So we'd expect a straight line that went up like this. And basically you get 1 mark for simply just drawing a straight line, and 1 mark for having a y-intercept and an upward slope. So it must be an upward slope because if the current increases, then basically the balance reading is going to increase. But it has a y-intercept because if we read the question, that when the current is 0, then the balance already reads 201.32 grams. It's not being zeroed or anything like that. Because I'm not sure what the mark scheme says, when it says sketch a graph, what I would also do is I would put on any numbers that I know. So I know, for example, when the current is 0, the mass in grams was 201.32. And when the current went up to 5, then the reading went up to 202.86 grams. So I'd put those numbers on. Now in this case, the mark scheme doesn't need you to do that, but but in an exam you don't know if they're looking for that or not, so I'd always do that. So that was question number 3 of the magnetic fields homework booklet.